Okay, we are moving on now to hypothesis testing when we don't know the population standard deviation. So for this, we're looking at a situation where the following conditions are met. We've got a simple random sample. The population standard deviation isn't known, and either the sample size is greater than 30 or the population distribution is approximately normal. When these conditions are met, as we saw earlier in Chapter 8, we use the student's t-distribution instead of the normal distribution, which means that our hypothesis test statistic is the t-statistic instead of z. It's calculated very, very similarly. We've got the sample mean minus the population mean, or the presumed population mean, what we're testing it against, the sample standard deviation, instead of the population standard deviation. So it's the sample standard deviation divided by the square root of the sample size. And the other thing we need to know to do the student's to use the student's t-distribution is the degrees of freedom, which is the sample size minus 1. Okay, so we need two things to determine, what region we're rejecting things, what region we're using to say, yeah, we can reject the null hypothesis. We need to know the type of hypothesis test and the level of significance. So for the type of test, we need to look at the symbol in the alternative hypothesis, greater than, less than, or not equal to. Remember that we are rejecting the null hypothesis if the sample falls within the rejection region. Okay, so let's talk about constructing regions with the student's t-test. Basic rules are exactly the same as with z-scores, except we're using the t-score instead of the z-score. Again, we'll reject the null hypothesis if t is less than or equal to the negative of the critical t-score for a left-tailed test. We'll reject if t is greater than or equal to the critical t-score for a right-tailed t-test, and we'll reject if the absolute value, that's positive or negative, if the absolute value of the t-score is greater than or equal to the critical t-score. So just a reminder of how to use the table, again found in Table C in Appendix A. You look at how many degrees of freedom you have, sample size minus 1, and you look at either a one-tailed or two-tailed test and what significance level you want for that. So if we're looking at a 5% significance level on a two-tailed test, we can look here at 0.05 and find, let's see, if we had 5 degrees of freedom and we wanted a 5% significance level, that would be our critical t-score. If we were doing a one-tailed test instead, and again 5 degrees of freedom, that would be our critical t-score. That table does have pretty much just the common significance levels, so 10%, 5%, quarter of 2.5%, 1%, half a percent. Yeah. As I mentioned, you look for the alpha you're after under the one-tailed or two-tailed, depending on which test you're using. Then find your degrees of freedom row and go till they intersect. All right, so let's find the critical t-score that corresponds with 14 degrees of freedom, meaning we had 15 samples, at the 0.025 significance level for a right-tailed hypothesis test. So right-tailed means we only want one tail. So let's see, we want 14 degrees of freedom and a one-tailed test. They intersect at 2.145. So there's 14 degrees of freedom, 0.025 one-tailed, intersect right there. Okay. So we have nurses at a teaching hospital who are complaining that they are overworked and understaffed. They think that the mean number of patients per nurse each shift is at least 8. The hospital administrators claim that the mean is less than 8. To prove their point to the nursing staff, the administrators gathered information from a random sample of 19 nurses' shifts. Sample mean was 7.5 patients per nurse with a standard deviation of 1.1 patients per nurse. Okay, so we've got nurses claim that they see at least 8, so greater than or equal to 8. Administrators believe that it's less than 8, so null hypothesis greater than or equal to 8, research hypothesis less than 8, sample size 19, sample mean 7.5, sample standard deviation 1.1. Want to use a 0.025 significance level, and let's assume the number of patients per nurse has a normal distribution. Alright, so what did the researchers want to gather evidence for? I did kind of give that away. The researchers are the administrators. It is important to note which direction you're looking at things from. If the nurses were taking this sample, we'd be looking at it from their perspective. This is looking at it from the administrator's perspective. They're wanting to show that it is less than 8. Right, so there's the research hypothesis that the mean is less than 8, which makes the null hypothesis that the mean is greater than or equal to 8. Right, so we've got a one-tailed test here. That's the other thing to note. In this case, the t-test is appropriate because it's about the population mean. It's normally distributed. We don't know the population standard deviation, and it's a simple random sample. Level of significance was stated as 0.025. So we can find our t-statistic as the sample mean minus the presumed mean divided by the sample standard deviation over the square root of the sample size. We get 7.5, we get negative 1.981. Okay, so as we noticed, it is a left-tailed test. It's only one tail we're looking at. We need to find the t-score for the rejection region. One-tailed test with a significance level of 0.025 and sample size minus 1 of 18 degrees of freedom. So we get a critical t-score of 2.101. Because we're after the left side, we'll use the negative of that, so negative 2.101. Alright, so here, next slide will show our graph. Our t-score of negative 1.981 was not less than negative 2.01, so we have to fail to reject the null hypothesis that which means that the evidence collected is not strong enough at the 0.025 level of significance to reject the nurse's claim in favor of the administrator's claim that they see less than 8 patients per nurse. Okay, now here's the fun part. The table in the book can't be used the same way the z-table can to find p-values. I could find the p-value range. So, for example, in the previous example, it was 18 degrees of freedom and 0.025. Where's that? Let me find the table. There we go. 18 degrees of freedom. And my p-value, my t-score was what? 1.981. So at 18 degrees of freedom, I can see that at 0.05, the critical t-value is 1.734, and 0.025, the critical t-value is 2.101. So I can see that my p-value is somewhere in between those two. So I can find the range of the p-value, which, as it shows right here, our actual p-value would be in that range. If we need to find it exactly, we have to turn to a calculator or Excel or something like that, just because that's not the way that t-value tables have been created. Again, using p-values, if the p-value is less than the significance level, you reject the null hypothesis in favor of the research hypothesis. If the p-value is greater than the significance level, you fail to reject the null hypothesis. Okay, so let's see an example. This is going to go through the calculator calculations. We have a local department store. It's done all its marketing, assuming that the mean amount spent by each shopper in the store is no more than $100. A new manager claims that the current mean is higher and wants to change the marketing scheme accordingly. So they talked to 27 shoppers at random and found that they spent a mean of 104.93 with a standard deviation of 9.07. So we don't know the standard deviation of the population, just the sample. They're assuming that the population distribution for amount spent is approximately normal, and they'd like to test the manager's claim at the 5% level of significance. We'll follow the same steps as if we weren't using the calculator. So the manager claims that the amount spent is more than $100. So that means the mean for our alternate hypothesis is that the mean is greater than 100. The logical opposite is that the mean is less than or equal to 100. So our null hypothesis is that the mean is less than or equal to 100. Alternative or research hypothesis is that the mean is greater than 100. As we've seen, the t-test is appropriate for this because it's about population mean. It's normally distributed. We don't know the population standard deviation, and it's a simple random sample. Significance level was stated as 0.05. Alright, so let's get all our things collected. Mean is 100. Sample mean is 104.93, so this is our presumed population mean. Standard deviation is 9.07. Sample size is 27. Stat, scroll menu, choose t-test, choose stats instead of data. Enter the null hypothesis mean, so that's 100. So we enter the null hypothesis mean, the sample mean, sample standard deviation, sample size, and tell it we want that we're looking for something greater than the null mean. Tell it to calculate, and it spits out our critical t-value, or the t-value for our group, and the p-value. So 0.004, which is much less than 0.05, so that so we reject the null hypothesis. P-value less than or equal to alpha, reject the null hypothesis. At the 0.05 level of significance, evidence supports the claim that the mean amount spent by each shopper in the department store is more than $100. Okay, next example. We have the meat packing department of a large grocery store. They put ground beef in 2-pound portions. The supervisors are worried that the machine isn't working right and that the mean weight of ground beef portions is not 2 anymore. So they randomly sampled 20 beef packages, and the sample mean of that 20 packages was 2.1 pounds with standard deviation of the sample standard deviation of 0.33. Is there sufficient evidence at the 0.01 level of significance to show that the machine is not working properly, assuming a normal distribution? Okay. All right, so the null and alternative hypotheses. The research hypothesis is that the mean is not equal to 2. So the null hypothesis, the opposite, is that everything's working just fine, and our mean should be 2. If everything was fine, the null hypothesis would be normal operation, right? All right, so the t-statistic is appropriate because it's a normal, random sample, normally distributed. It's about a population mean, and we don't know the population standard deviation. The desired level of significance was 0.01 or 99% confidence level. Remember, confidence level plus significance level equals 1. All right, so we get the sample statistics. We've got mean, presumed mean of 2, sample mean of 2.1, sample standard deviation of 0.33, sample size is 20. Again, we go to the t-test in the calculator, select stats, tell that we're giving it the values instead of entering the raw data. Enter the mean for our null hypothesis, sample mean, sample standard deviation, sample size, tell it we're doing a not equal to, have it calculate, and we get a p-value of 0.19. And 0.19 is greater than 0.01, so our p-value is greater than alpha, so we have to fail to reject the null hypothesis. It's not strong enough evidence at the 0.01 significance level to say that the machine isn't working. It's not to say that the machine is working just fine, it's to say that we don't have the right evidence to show that it isn't. It might be time to, go back and do more sampling. All right.